So we're going to start with some early ideas of how Earth can change. This is an evolution in thinking of what the Earth is and what's going on beneath our feet. This video is going to focus on the early ideas for how Earth could change, and then this sort of culminates in this continental drift hypothesis, which I think you've heard of before. You might be surprised to know that this theory was actually rejected initially. So we'll talk about what's going on there, why it didn't catch on when it was first proposed in the early 20th century. So stepping back, there's probably lots of places on Earth I could show instead of the Grand Canyon in Arizona, but this is a pretty classic place in terms of something that has caused people to come in and wonder what's going on with the Earth. How old is it? How is it formed? What shapes it? One of the things that's remarkable about the Grand Canyon is that you have cliffs that are thousands of feet tall, not that far apart, and this small Colorado River running through. So this sets up two really different ways to think about how such a feature could have been formed. Is this something, can this slow and steady Colorado River, can that actually erode this giant canyon? Or do you need some giant event, some kind of mega flood to come through and carve out these walls, and ultimately what we're seeing today is just a small trickle of that. So these two perspectives, you can say, are really encapsulating these two different worldviews that characterized early thinking before Earth science really became a science. There's this legacy of what's called catastrophism, the idea that Earth was created and shaped by these singular cataclysmic events. You can see the word catastrophe here. Examples of this include Noah's flood from the Bible, which was originally invoked to explain things like the Grand Canyon, but also how different mountains were formed, how the oceans were filled. There's a lot of different processes that were originally blamed on the flood, even though there were some inconsistencies being piled up. For instance, there were fossils in the Appalachians that are hundreds of million years older than the fossils in the Rocky Mountains. So, and overall, the idea of catastrophism was consistent with an estimate of a young Earth based on the number of generations outlined in the Bible, which put the Earth at around 5,000 years. This was sort of the officially sanctioned age of the Earth for a long time. It's been replaced by more scientific methods that show the Earth is a lot older. And so even though catastrophism was the default explanation for much of, for a large part of the last 2,000 years, especially in Europe, this idea of uniformitarianism has taken place as sort of the more scientific view. And this is because, in order to explain something like the Grand Canyon, we need to measure similar processes happening today. So if you measure how much sediment is in the Colorado River, that's sort of an estimate of how much erosion is taking place on that river path. So maybe if you take that sediment that's being exported by the river, multiply that by 10 million years, 100 million years, a billion years, can you actually account for the total size of the Grand Canyon of the missing Earth? So that's sort of a uniformitarian view of this, is that every process that has shaped Earth in the past is still happening today. So the thing is that this requires a much older Earth. So this is before you have the radioisotope measurements that we talked about previously from meteorites, from zircons, from other Earth archives. But with the sort of shift in thinking here was once catastrophism became out of favor, it was the idea that there was this shrinking Earth theory was sort of able to explain a lot of the major parts of Earth's surface. This is the idea that Earth is slowly cooling, it's losing heat to space from its core, through its mantle, through its crust, out into space. And as things shrink, they become smaller. So as the Earth loses heat, it shrinks a bit, but just like an apple, or the analogy is similar to an apple here, its crust is the same size. So if you ever had an apple sit for too long, you might notice that it's a good-looking apple at the first, and then it starts to become a little bit smaller. Its skin gets a bit wrinkly. What's happening here is the apple is losing water, and then its skin is the same size, so it starts to wrinkle up. And that was what was proposed to happen for Earth, was that the Earth was cooling, so it was shrinking, but the crust was the same size. So then you have all these different folds forming The first and biggest folds were ocean basins and mountains, and then other ones were sort of the small hills and other things that you would see around town. So this was something that it seemed like was a process that was still happening today, so it could be observed. And so this coincides with this kind of age of exploration where people were able to look at Earth in a more holistic and synthetic way because they had access to much larger parts of the planet than in the past. And what you see when you go around the world is these similar sedimentary rock features. And this was consistent with this idea of a shrinking Earth because you could have something that was obviously laid out underwater in the past. That's what you need to have these sort of slow rain of debris and material stack up. You can see each of these images has like these sort of layers here, but some of them are at the top of the mountains, some of them are these sort of smaller hills, some of them are rising out of the ocean. But in all these cases, the higher parts of this are the younger parts, the more recently sedimented parts of these rocks. In the bottom part, these are the older parts. So you can kind of go from the past to the future, or at least to something less in the past here. And in all these cases, this is Glacier National Park in Montana. This is obviously the top of a mountain. These are these cliffs rising out of the sea in Sicily. You can see these sort of similar stripes here. Las Vegas, these are some really stunning cliffs in China. So the Earth is sort of full with these exposed sedimentary rocks, and so the idea was these were sort of potentially aquatic features before, and then because the Earth was shrinking and creating these wrinkles, they were exposed today. But there's still a lot of areas of the Earth that don't really fit into this simple model. This is a great example here from Tel Hierro Beach in Portugal. What you're looking at here, if you take a second to just peek into this, you see you have some sedimentary rocks that are clearly folded up and down here. These are Carboniferous rocks from the Carboniferous period of Earth. They have there's coal in there. They're carbon rich. They're probably formed during cold climates, and they're obviously have been smushed together and subject to intense pressures and geological events that have been making this into this big zigzag instead of a flat stack of sedimentary rocks that they probably started as. But then these are overlain by these flat Triassic red sandstones. These are formed by the same processes that occur here on Hawaii. If you've seen the red soils of West Oahu, Molokai, any dry part of any of the islands here, these are the soils that form here. They're washed out. They're stacked up in at a river mouth or something, and so these are a bit younger, but they're still pretty ancient. They have ancient fossils in them, and you can see they're just flat. So obviously these had to be stacked, put into place after this folding had to happen. And so this was a challenge both to people who were holding on to the idea that the Earth was 5,000 years old, because it's going to take a lot more time to lay down that first, Carboniferous set of rocks, slowly squish them all together, have basically 50 million years of missing sediments there that got scraped off somehow, and then start putting in new things sort of flat here, and then obviously lift them up onto land so you can see them. So it's a challenge for people who believe in the young Earth. It's also a challenge for people who were holding on to the shrinking Earth theory, because this is a lot of different modes of action, and if the Earth is continuously losing heat, you need a lot of different processes in play, not this slow growing of wrinkles. There's another example of this in the Grand Canyon here. These are Proterozoic, red clay sedimentary rocks. You can see that these are all found at an angle today. They were obviously laid down flat underwater. They were picked up and put on an angle here. Sorry, the camera's inverted. And then there's hundreds of millions of years missing here, and then you have these later Paleozoic sediments that are obviously found at a different angle. God, this is so bad. Okay, an angle here. These have multicellular life. They have fossils of invertebrates, and so obviously there's tons of time in between that's just totally missing here. That's what's called the Great Unconformity by geologists, and obviously you need tons of time to lay down each of these sedimentary rock sequences. This is hundreds of feet tall. I mean, how long is that going to take? It's going to take a long time. And then the last thing that was a real challenge to this idea of shrinking Earth was the observation that different fossil species were found across different continents. So this is the great example here are the mesosaurs or Mesosaurus. This is an aquatic freshwater reptile that lived in the Permian time. We now know this is 300 million years ago based on radioisotope calibration of these different fossil assemblages. But this is a picture of them. They're living in freshwater environments. They're eating freshwater fish. They need fresh water to live. So obviously, if you can imagine a river system, right? The Mesosaurus can travel between one tributary of, let's say, the Amazon to another tributary of the Amazon, no problem there, right? But then how do you have the same fossils found over in Africa, right? If they're not found anywhere in the ocean, then they're probably not swimming across this distance. So this was a challenge. So you had identical fossils found in Brazil and in Namibia. So how can you have the same species be in two very different places at the same time without any evidence of ocean life? And so this was one of the pieces of evidence that this German meteorologist, Alfred Wegener, was thinking about when he proposed this idea of continental drift. So this is where this word Pangea comes from. This is a word that we all know, and he sort of remarked that isn't it weird that the Andes, that South America, Africa, North America, Europe all kind of fit together. He wasn't the first person to do this. I mean, people had been doing this since the first maps of the world were made. But he was one of the first people to take this seriously as a way the Earth could have been in the past. And so this plus this observation that you had similar fossils in South America here and also in South Africa here, this seemed to make sense that you had this Pangea in the past where all of the land was pushed together. And then less often talked about is this idea of Panthalassa that's obviously covering the rest of the globe, this global ocean that's connect from here and extends all the way around the globe over to here. So what other evidence did Wegener use to look to argue for Pangea? Well, it wasn't just the Mesosaurus fossils. There were also consistent, very similar rock types found on both sides of the Atlantic Ocean. This is there's a singular mountain chain that are now forming the Appalachians here, or the Appalachians are the relics of this older mountain chain. But the same mountains are found in Newfoundland, in Canada, in northern England, in Scotland, in parts of Greenland and parts of Norway. So it seemed like these mountains all had to be sort of aligned together if they were from the same origin. At least that could explain why you would have similar rock types, along this large distance. The other thing is that these are older than other mountain chains. So the Alps, the Sierra Nevada, the Himalayas, these all had much younger fossil assemblages, in their various strata. And shrinking Earth theory kind of says that all mountains should be kind of the same age if Earth started shrinking at a similar time point. And then in addition to fossil evidence, in addition to the geological evidence for similar mountain chains that could have been formed together, there's also this paleoclimate evidence. And this is a bit strange. There's two key parts to this. The first is that in Northern Europe and Greenland, there were coal deposits found, or there are coal deposits there today that were formed from tropical forests. This is a process of bituminous coal is the vocab word for this. But these are only formed in tropical environments today, but there's evidence that there's deposits of these in Greenland and Northern Europe. They're also found in some places in Antarctica. So these places were obviously not at the poles in the past. They had to be towards the equator. Also in equatorial Africa and South America and Australia, there was evidence for what's called glacial striations. These are places where giant glaciers were sort of flowing through and carving out the bedrock, leaving these big kind of gashes in the side of the rock. And obviously, then these are on the equator. So obviously the Earth had to be arranged in some other way than it is today, where you had parts of South America, parts of Central Africa, parts of India sort of subject to ice sheets and glaciers, whereas you had parts of Northern Europe here in the tropics. So these tropical forests could start laying down carbon, which can turn into coal. And then, as Wegener was proposing this idea, he drew not only from the Mesosaurus, he also connected this to a couple other fossil groups here that were extending from both South America to Africa, or from Antarctica through India into Africa. So there were other fossils from both animals and plants which could explain this arrangement of the continents, that you had this Gondwana land of South America, Africa, Antarctica, Australia, India, all sort of set up together. And a lot of these guys aren't even aquatic at all. So maybe you can imagine the case for Mesosaurus to, I don't know, have some strange journey across the Atlantic a long time ago. But I mean, these guys aren't moving. You've got plants that aren't moving. So it makes more sense for these to be connected. So this is convincing, right? I mean, this is, it seems like there are fossils, there are mountains that argue that the Northern Europe and Africa and North America were together. There's these fossils that are shared across all the southern continents, which must have been pushed together. And so Wegener sort of put this together as this idea. He said, I think I figured this out. And then ultimately, no one cares. I mean, this idea was not accepted at all. Wegener was ridiculed. And it's unfortunate, but it's sort of what happened. Why did people not like this idea? Well, first off, the central problem with Wegener's version of continental drift was he didn't really explain how this could happen. Right? He said, okay, well, the continents could fit together, and there's other evidence that things fit together, but how did the continents move apart to their present condition? What was the force driving this? And admittedly, this is sort of unsatisfying. Wegener had this idea that there could be some, because of the rotation of the Earth, it was sort of flinging the continents out. Sort of, if you have a ball on a string, it would sort of end up towards the equator. But no one really bought this. This doesn't really make a lot of mathematical sense if you try to do diligence on this and check it out. But a potential way to check this idea too is, even if the math is wrong, is that if the continents are drifting, right, then maybe they would leave tracks in the seafloor. Like, if you imagine kind of like a snowplow, we have this sort of front end that's covered in sediments, and then the other end that's sort of has these trail marks behind it. People didn't really know what the seafloor looked like this time, so this is a potential prediction that could prove Wegener right. But also, there's a culture clash here. Wegener was a meteorologist. He did most of his work in Greenland, studying glaciers and studying the weather in the poles. He wasn't sort of part of the geologic establishment here, and so when he proposed this idea, he just seemed like some kind of crackpot who just was coming in, not really knowing how things were done, and his critics sort of pounced on him. Ultimately, Alfred Wegener died in Greenland unexpectedly during field work on a glacier, and so he couldn't really champion this idea anymore. And without him thinking he was right, no one else really thought he was right. And so this was the rejection of the continental drift hypothesis. And so I think ultimately, just to sort of spoil the story here, this turns into this theory of plate tectonics, but it's not a one-to-one thing. Continental drift and plate tectonics are not the same thing. There's sort of an evolution of thinking here. An important thing to realize is that continental drift was conceptualized by Wegener without really any kind of understanding of the ocean floor, and this becomes really key in terms of making things make sense for thinking about how the continents could start moving in the past. Okay, so to wrap up, in this video we've compared uniformitarian versus catastrophic ideas for geologic change, and we've discussed the evidence that was sort of moving away from how people saw the world in the 18th century and the 19th century into this idea of continental drift, which eventually moved into plate tectonics, but was initially rejected. So I would study these factors here when you're thinking about how to review this material, and I'll see you in the next video.